Welcome back to James's Physics 101. Today, we're diving into the jewel of physics, quantum electrodynamics, or QED. This theory explains how light and matter interact with mind-bending precision. It's the foundation of modern particle physics. In 1965, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga were jointly awarded the Nobel Prize for cracking this code. But before them, physics was in a state of crisis. Earlier equations kept spitting out infinity for the self-energy of an electron. The breakthrough began in 1947 at the Shelter Island Conference, where experiments proved these subtle effects were real and required a consistent theory. The core idea of QED is that the electromagnetic force isn't just a field, it's an exchange of discrete particles. We call these messengers photons. They are the gauge bosons that carry the electromagnetic force between charged particles. Specifically, these are virtual photons. They pop in and out of existence just long enough to transfer momentum and carry the message. Every interaction in the universe happens at a vertex, where a charged particle emits or absorbs a photon. To calculate these complex interactions, Feynman invented a revolutionary pictorial language, Feynman diagrams. In these diagrams, straight lines represent matter particles, like electrons, carrying their mass and charge through space-time. Wavy or squiggly lines represent the photons, the messengers that mediate the electromagnetic interaction. The arrows indicate the flow of time and charge. An arrow pointing backward in time, that's an antiparticle. Feynman's radical insight was that a positron is just an electron moving backward in time, a stunning simplification of nature. These aren't just doodles. Every line and vertex in a Feynman diagram corresponds to a specific, complex mathematical integral. This is based on Feynman's path integral formulation. In the quantum world, a particle takes every possible path from A to B simultaneously. We find the final probability by summing the amplitudes of all these paths, a method known as the sum over histories. Each path has a different phase and amplitude. Like waves on a pond, they can reinforce or cancel each other out. To fix the original infinities problem, Feynman and his peers developed a technique called renormalization. By accounting for the cloud of virtual particles that always surrounds a charge, they could calculate finite, physically meaningful results. The result? QED is the most precisely tested theory in the history of science, matching experiment with uncanny accuracy. Take the magnetic moment of the electron. The theoretical prediction matches the experimental measurement to more than 10 decimal places. That's like measuring the distance from New York to Los Angeles to the accuracy of the thickness of a human hair. QED served as the blueprint for the entire Standard Model. Its framework of messenger particles was later applied to other forces. The strong force uses gluons, and the weak force uses W and Z bosons, all following the rules Feynman first laid out for light. Feynman was more than just a Nobel laureate. He was the great explainer, known for his infectious joy and bongo-playing spirit. So, photons as messengers, Feynman diagrams as our map, path integrals as our engine, and precision beyond compare. Quantum electrodynamics truly is the crowning achievement of 20th century physics, the jewel in our scientific crown. Thanks for watching James's Physics 101. Be sure to check out the rest of our Particle Physics in 10 Micro Lessons series. Master the pieces and you master the universe. I'll see you in the next lesson as we explore the Higgs boson.